And this is water resource change. As you can see here, this is positive number, so that more precipitation in the south over this peninsula, and less precipitation and drought. This is very consistent with what Manjaro showed. So that, there is many uncertainty over here in this peninsula. So we have to identify what's going on over here. And for the economic growth, overall global economic growth from mid-90s to present, as you can see, all increased, significantly increased after 1990. And this amount is insured. So the finance community is very much interested in our science because of predicting the economic growth. In general, significant increase of economic growth over the globe, but also the interannual variability is very large. So that finance community is very much interested in this information. So we have to have a prediction tool. That's why we need a climate prediction system. And climate prediction system consists of many things, but most important thing is climate model. Of course, supercomputer we need. And as previous talk about observational data, global observational data is needed for initialization of the model. Altogether, we can make a climate prediction system. Today, I'm going to focus on global climate model. And the computer model consists like this. Globe, the Earth is divided by many grids, like this. And then each grid is represented by a mathematical formula. And the mathematical formula that we are using is the fluid dynamics equations, momentum equations, and thermodynamic equations, and continuity equation, and other equations. But this is major equation. And all those processes in the climate system are expressed in terms of the mathematical formula, and all those are interactive. So it is a very complex system. And I'm not going to talk about the detail, but this is very complex system, and all those solar radiations and cloud and cryosphere and ocean and here this is example sea ice and land surface, all has to be expressed in terms of mathematical formula, and those are interacting with each other. So that it is a complete one system. So we are playing this system, and we are going to develop the system like this in this university. And we need to do this, we need a supercomputer, of course. The first computer, which was created in Princeton in 1946, which applied first to weather forecast. And then the weather forecast and climate scientists actually pushed computer industry to make faster computer. And in year 2000, our simulator was created in Japan, which with this we can do many things. And this is an example, so that after this, many operational centers and supercomputer centers makes upgrade our simulator. Now KMA has Korea. KMA has about 20 times bigger than our simulator, and many countries now has a big supercomputer to use for the use of climate prediction and weather forecast. Right now in KAU, Sungrade, which is about 3.3 teraflops. about 1/5 of this Earth simulator. But this Earth simulator was 10 years ago, okay? And we are currently in the center has 1/5 of Earth simulator, so that this computer is already saturated with few months. I will show why it is already saturated. The current state of global climate model. Actually, I'm involving in this development internationally and in my university, and I'm going to show what I am doing and what I am going to do here. This is the uncertainty of climate model. This is satellite figure of the crowd. Okay, two different figures, and if you image this in terms of the model grid. This is like this. Okay. If you have, very high resolution, then we can create the image like this. But currently, with current climate model, the image is like this. So that if you compare these two, there's significant differences. So this is our current state. This is mainly because of our computing facility. And this is one of the example. This is our model with 300 kilometer resolution, and 100 kilometer resolution, and 25 kilometer resolution. And this is observation, a satellite observation. As you can see, 300 kilometer resolution, 3-hour snapshot animation. If you compare this one and this one, there's a big difference, right? And surprisingly, IPCC current climate models that Gaston showed in previous talk, they all use this resolution. Okay, so current climate model is in the state of this. Okay, and one exception is current AR5 IPCC. One exception is 100 kilometer resolution, which is from Tokyo University of Tokyo. They submit their simulation results with 100 kilometer resolution. Okay? And all of the other 20 some operational centers and climate modeling center submit the data like this, 300 kilometer resolution. But this is why. Our simulation and prediction is so uncertain. Okay? We must go to beyond 25, beyond that. And but because of this computational limitation, we cannot make 10-year simulation. This case we made about few months. Okay? But we have to simulate with this kind of resolution for 10 years, 100 years. So this is why we did a supercomputer. With this, this 25 kilometer resolution simulation has been done 2 years ago in my institution using KMA supercomputer, which is about 20 times faster than our simulator. Okay, but still limitation for doing this kind of thing. And here, we are going to target on this resolution, not this resolution, okay? So that we are strictly straightforward to international level. And previously, Carson talked about the importance of ocean. Ocean is very important because of it has memory, so that we have to couple ocean and atmosphere together to predict seasonal prediction and to make seasonal prediction and climate predictions. So this is the model that we are using. This is coarse resolution, and this is medium scale resolution, and this is 25 kilometer resolution in the ocean. And as you can see, this is the phenomenon of the ocean waves, which is currently observed with a high resolution observation. And this is the simulation that we did with 25 25-kilometer ocean model, as you can see, there are many structures. Okay, so that we must use this kind of model in order to keep this kind of features coupled with the atmosphere with equivalent resolution. And this is one example that why we need high resolution. This is a TRIM satellite observation, and this is 300-kilometer resolution. Our current model are similar. There is some similarity, but as you can see, very broad rainfall structures, and 100 kilometer like this, and 25 kilometer now it shows the regional features. So that in order to focus on the regional features, we need this kind of resolution and this kind of model. But as I said before, currently in the international community and WCRP as a whole, because of computational resources, we have to use this kind of resolution. I mean, I'm showing this is just for the example. In order to accomplish the WCRP requirement, we have to make a simulation for several thousand years. Okay? So that with this kind of model, it is impossible with current computer. Okay? So this is why, I mean, right now, many institutions has technology and science to go beyond this. Okay? Many institutions has such kind of science, but we can't because of computer resources. But I think Saudi can do it. And when I talk this kind of supercomputing power with K president, he said, I mean, even this university can provide the supercomputer. I mean, high-level, world-top supercomputer. So there is a big hope in this university. And this is the moisture transport, which was measured, kind of a satellite product. We are here, okay? This is the Arabian Peninsula. This is moisture transport, so that which creates precipitation, rainfall. As you can see, I mean, all dry, but sometimes there's a storm goes in, okay, as you can see, and sometimes this moisture transport goes into the Jeddah area. So this area is very sensitive, okay? Very dry and wet in the boundary, very in the boundary. So that in order to represent this kind of feature, we need high resolution, okay? Otherwise, I mean, all uncertain. Okay? This is our reason, which is sensitively respond to this kind of very wet and very dry. So we are in the boundary. And this is our global crime model, and the low resolution and high resolution. This is a simulation capability now. This is stream observation. This is two observation. Even two observation is a little different. And this is our current simulation capability. As you can see, you can compare and you can judge of this model. 25 kilometer high resolution and 300 kilometer. As you can see, there is certain differences. And this model, although there is some excessive precipitation over here, in general, this simulation quality is not too bad. So we are working on this. And this is a typhoon simulation. As Hassan mentioned, that most important these days is extreme predictions. I mean, insurance company and the government is very much wants to have information about extreme predictions.